So my students and I have been trying to understand dynamics for robotics and reading this excellent book by Lynch and Park, which does everything with wrenches and twists. And but today I thought I'd look at just statics. What is the sort of combination of forces and torques in a structure that keep the structure from moving? So that's known in mechanics as statics. And I always had a hard time with statics because it seemed to require a combination of creativity and experience. And I remember having a hard time in college. But no more. Based on the book by Lynch and Park, I figured out a way for myself to do statics with wrenches. And it's also a good way to introduce the use of GTSAM as a sparse linear solver in this context. So I created this little notebook to explain statics with wrenches. So I call it a wrench recipe for statics. So here's a little notebook I created. I already installed GTSAM. It's Python, so I'm just going to evaluate the cell to get a bunch of libraries. And so here is the overall recipe that I'm going to use. And it's simple. So if we have a multi-body system, like a robot, we'll do mostly planar examples here. For every joint, you define a parent and a child link. So that's what you start with. Then we define a single unknown wrench for each joint. And this is defined as the wrench exerted on the child link from the joint. Okay. A wrench is, in 2D, it's just an X and a Y force and a moment around the Z-axis that comes out of the plane. In SE3, in 3D, it's going to be 3 forces and then 3 torque components. But this notebook is going to be using exclusively SE2 code examples. We only need to introduce one unknown wrench per joint because if you have the parent link, the wrench exerted by the joint on the parent link, which we don't explicitly represent, is just the inverse of the other wrench. So of the wrench on the child. So the wrench is expressed in the child frame. So the cool thing about wrenches is that you can express them anywhere. You can move them using something called an adjoint, which is sort of a Lie group theoretic thing. It's just a matrix. In SE3, it's going to be a 3x3 matrix, and we can move it to any coordinate frame. So we can represent the wrench wherever we want. We're going to choose to do that in the link frame, but the link frame is arbitrary. So here I'm departing a little bit from Lynch and Park, where people, where they say, you choose the link frame in a particular way to make the equations easy for articulated robots. But I'm going to say, choose the link frame wherever you want it. At the center of mass is what I'm mostly going to do, because that's where gravity applies. At the joint itself, even a stationary frame outside the link is fine, because it's static. We're not moving here. And then finally, we're going to write one equation per link, which is to say that the link is in balance. So we're taking all the wrenches that apply to that link, convert them to the correct frame, to a similar frame. We're going to do it to the link frame, and then that gives an equation, and this will solve the entire system. By the way, this strategy solves all the examples below and is a generalization of what I read in Lynch and Park. But it could be that this is completely well known in mechanics, and I'm just giving 101 textbook example here. That's fine. I've not found many texts, and I don't own any 101 ME texts, mechanical engineering texts. But if you do, and you have you can tell me where this is described in this way, then please let me know, then I can add a reference. And I'd be interested in reading about it. Let's start off with a very simple example. Okay, so here's a single link. I call it the body, connected to the stationary frame using a revolute joint. And so for every joint we introduce an unknown. So I'm going to assume, by the way, that the joint is actuated, so it can resist forces, 2D forces. Okay, and it can also resist the torque by having an actuator there. So this is different from a pin joint, which cannot actually deliver torque, right? So if you apply our strategy, okay, so I'll put the drawing in the strategy. We have joint 1, and we'll say that B is the child and S is the parent. So we introduce a single unknown wrench, which is a 3D quantity, Fx, Fy, and the torque, or the moment. And that is the wrench exerted on the body, okay? And it's expressed in the body frame. I'm added this this frame here, this link frame that is aligned with the joint, with the link. And then we have one equation per link. There is only one link. We're going to not consider an equation on the stationary frame. And that has to be 0. There's no gravity here, so it becomes very, very simple. Okay, so it says that this wrench better be 0. Okay. All right. So that was easy. We're saying basically to make this link static, we should not apply a wrench. So wherever we put the link, we can have a static balance here, because there's no forces, there's no reaction forces, right? So that was just to introduce really the strategy in a very simple example. Let's go to a little bit more interesting example. So here we have the same link, but now gravity is applying to the center of mass. I've chosen here to rotate the link frame. That was silly of me, because now we have to write the wrench due to gravity with sines and cosines, right? But it's not too hard. So if you assume a mass of 1 kilogram, then we have in x we have minus cosine g. So this is a projection of that red onto the x-axis, and we also have a minus. Sorry, it's sine for cosine and sine for x and cosine for y. You can verify that for yourself. And I've written the wrench out here, and note that I'm going to write all wrenches as row vectors. I have a particular reason to do that, but I'm not going to go into too much detail. It involves tensors and Einstein summation. All right, so let's see. So now let's apply the recipe. We introduced the same wrench, but now the link balance equation reads that the sum of the wrenches has to be 0, and we have this extra wrench, the gravity wrench. So the outcome is going to be that the wrench applied by the joint on the body, expressed in the body, is just going to be the negative gravity. Okay. So we have to cancel gravity. All right. That's also easy. You might wonder what then the torque is that has to be delivered by the actuator. And if you look at the gravity at this wrench, right, if I go up a little bit, you see that the torque here is 0. And in fact, indeed, gravity is just a force, so expressed in the B frame, there is no torque created by gravity here. But to calculate the torque delivered by the joint, we have to actually transform the wrench to the torque frame. So let's show you the math here. So okay, so we need to use the SE2 adjoint map. All right. So here this is written as the wrench in the joint frame, so I'll call that here J1, is the wrench in the body frame times this 3 by 3 matrix. Note that the wrench is a row vector and this is a 3 by 3 matrix. So if you would consider this as a column vector, you have to multiply on the other side and transpose this. But writing it this way, we can just write it on the left. And so we calculate that wrench in the joint frame just by applying the adjoint. And then the torque is just the third element of that wrench. So we multiply it with the unit vector 0, 0, 1 on the right, and we get the torque out. Okay? And so to make this simpler, I'm going to introduce two different notations here. One is, it's sort of annoying to have to write adjoint as a matrix, etc. So I'm just going to add this shortcut notation, add AB, that maps wrenches from B to A. Okay, so how do I know it maps wrenches from B to A? Because if I have a wrench in B, which has a subscript, then it cancels the superscript here, and I'll get out a new subscript, which is a wrench. It indicates a wrench in A. I'm also going to take the concatenation of the adjoint and the K vector here as I'm just going to multiply them. And what I get out is actually a 3 vector, it's a column vector, which does both the adjoint and the extraction of the torque in one go. And in Lynchian Park, this is called the screw axis. And so now we can this is a screw axis for a joint rotating around the z-axis. So we'll abbreviate that ZBA. And so if you want the torque from a particular wrench in a particular joint, we just multiply it on the right with this z thing. And now let's do this in code. So this is going to be our first code example. Okay. So let's define a little function, wrench, which creates a row vector. It's just that I don't have to write np array float, etc. all over, and also to sort of enforce the fact that it's going to be a row vector, which you might otherwise not do. Of course, NumPy actually doesn't care whether it's a row vector or a column vector. It's particular like that. Then we add our constant for gravity. I'm going to use 10. Adjust to your latitude. There is nowhere on Earth where G is 10 actually, but G does vary according to latitude. The closer you are to the equator, the smaller G will be, which is interesting, right? So then we say let's take a joint angle of 60 degrees. We create our gravity wrench. We then have our resultant wrench, and then we print it and let's see what happens. So actually, let's evaluate it. All right. So the wrench is in the body frame is 8, 5, which are just plain forces, and in the body frame there is no torque. Okay. All right. I'm building some machinery because later I will need it. For this one, we really don't need it, but I'm going to add a dictionary here to store all the coordinate frames I need. And when I insert something into the dictionary, it's going to also insert the inverse, so I don't have to bother with inverting. So let's do that, and we get, so here we start using GTSM. So I use GTSM pose2, which is the type to create an SE2 component in GTSM. Note the order, we use X, Y, and then orientation. And for SE3, we actually do the opposite in GTSM. That's historical. The roboticists like to think about X, Y, theta in the plane. So I use that notation. So this dictionary here has all these different frames, so from the body to the joint frame, from the joint frame to the body, because that's there, from body to stationary, etc. So all of these we have. I also composed SJ1 and J1B to get, so I have these intermediate frames as well. They're probably not needed in this simple example. So with this in place, we can start transforming wrenches and then calculate the torque. So lots of machinery to do a very simple thing, but we will use the machinery later for more complicated things. So applying this, so I actually introduced also two little functions: add, which calculates this 3x3 matrix, and z, which calculates the wrench matrix. Always, taking a wrench in B and producing something in A. So that's why the order of these initials is like that. So we multiply these things again on the right with the wrench. Right. So here we calculate the torque. We have our wrench that we computed, and we multiply it with the screw axis that goes from B to the joint frame. Okay. And we get 5, so 5 Newton meters, and you can verify that that is in fact indeed the torque. If you look back at the example, here we this is 60 degrees, and it's 1 kilogram, so this is 10 newtons. I used 1 for the length here. So this is a half, so the moment is simply you just have to take the arm perpendicular to the line of application, which is 0.5, and 0.5 times 10 is 5. And this is, by the way, in the gravity induces a counterclockwise moment, so the joint has to go the opposite way. So let's verify that the torque delivered by the joint is indeed 5 Newton meters, which is counterclockwise, and so that's correct. Cool, so this is the whole machinery. I think now we will just run through some examples that are a little bit more complicated, but I'm going to go back to the original recipe and restate the recipe. And so it's very simple. For each joint, you define a parent and a child. You define a single unknown wrench that acts on the child, and you express it in the child. And then for each link, you create you write the wrench balance equation down, and then you can hopefully solve for all unknown wrenches. Or can you? All right. So let's now look at some examples to see whether this can be applied in general. So let's do the canonical Lynch and Park thing first, which is let's take an articulated arm. All things can be explained using just a 2-link arm. We have a link A and a link B. We introduce 2 unknown wrenches. The wrench applied, so I indicated this with this little green thingy here. The wrench applied on link A, expressed in link A, wherever I put the coordinate frame, okay? The wrench applied by the second joint, joint 2, on its child, which is link B, so I express it also in B, and those are my unknowns. The green wrenches that apply on B, of course, have an opposite reaction on the parent link. Here on A and here on S, which will just be resisted. Okay, doke. So, what about the reaction to gravity? Now we have 2 balance equations. 1 in B, so I wrote that first, which is if there is just a gravity here, which I didn't draw, but here is a gravity wrench in B, and this is the same as before. But now we have this other link, so we have the joint one has to resist gravity, but we're helped or hurt by the opposite, the reaction wrench, okay, from joint 2, which is written here as minus FB2. But we have to convert it to the A-frame because this link balance equation is summed in the A-frame. So we multiply with this adjoint on the right. So row vector 3 by 3, and so this works out. And this is our system of equations. Now you might wonder, can we actually solve this? How many degrees of freedom do we have? Well, we have 2 unknown wrenches. This is SE2, so each of them has 3 unknown coordinates. And how many equations do we have? Well, each one of these is a vector equation. That's, a 1 by 3 vector equation. So that's 6 unknowns. So it seems that we can exactly solve for the statics in this case. All right. Let's do it. Okay. We're just gonna insert some pauses in our dictionary. Okay, so between A and the stationary frame and B and the stationary frame. And I eyeballed in this case let's look here, the A and B. I said, well, it's like 0.5 and what did I say? 1 and the next one is 1.5 and 2.5. I really just eyeballed the middle of these wrenches. Sorry, of these links. I keep confusing the two words, but the middle of these links, that's where the COM is. And if the COM, if it's not exactly the middle, that's fine too. We can always distribute the mass in the link to make it a COM, right? So I'm always right. Let's go and then add a gravity wrench. Now, something else I did is I said the following. I don't care to align the frame with the link. I'm just going to make the link frames horizontal, because then I have to deal with cosines and sines, and that is totally fine. You can choose your link frame however you want it in a statics problem, okay? So we just choose it to be easy in this case with all 0 angles. And then we can just say minus G, assuming again 1 kilogram links. And now we're going to solve the system, and that can be easily done by hand. Okay, so first we actually have to insert 2 more clauses here in our dictionary, because we will need the adjoint for BA. But this is solving the system. We just have the wrench in B is going to be the opposite of the gravity, and then the wrench in A is going to be the wrench applied by joint 2 multiplied with the adjoint, and then minus the gravity wrench, and we can just easily do this. So let's evaluate this cell to get the wrenches and solve the system by hand. And the example is quite simple. We have B just cancels gravity, and in A we have to cancel the gravity of both links, so that joint has to carry both. It's 2 kilograms, which is 20 newtons. It's up. 0 reaction force in Y, because nothing is happening in Y. And then that joint also has to keep the entire arm from rotating, so it has a counterclockwise moment. In A, that is not yet the joint, so to actually look at the torques in the joints, we do the same as before, right? We're just going to use the Z function, which gives us the screw axes. Shift enter, and we get 20 Newton meters in the first joint and 10 Newton meters in the second joint. And that keeps the whole arm up.